In the previous video, we have learned two different ways to calculate total work done. First is by summing up the work done by individual forces that are acting on an object. Then the second way of determining work done is by finding the net force first, then doing a scalar product between the net force and the displacement that occurs. So both methods will give us the same total work done. And for this video, we are going to focus on the second method of determining work done, which is by using this formula here. So work total is equal to the scalar product of the net force and the displacement. And if you change it into another form, it will be the magnitude of net force multiplied by the magnitude of displacement times cos theta, where theta is the angle between the net force and the displacement. So we have seen this kind of equation in the first video where we talk about work done by individual forces using equations. So we know that this equation here can generate answer which can be positive, 0 and negative. And we know that the positive, 0 and negative here depends on what is the value being generated by this cos theta behind here. Because the magnitude of net force and the magnitude of displacement here are both positive because they are magnitude of a vector. So these two parameters here can't be negative. So if you get 0, you get negative, it's because of the cos theta behind here. Okay, so for the situation where your work total is positive or work total is greater than 0, it's because your cos theta generates a positive value. So how does a cos theta generate a positive value? Your theta here, your angle between the net force and the displacement, have to be in the range of 0 to 90 degree, but not inclusive of 90 degree. So that will be the range for your angle. And if your displacement is pointing to the right, you should expect your net force to be in this direction, the same direction as the displacement, or it can be anything like this, as long as if you resolve this net force, it has a component that point in the same direction as the displacement. Then your work total will be positive. But in our syllabus, because our focus is only for straight line motion, we'll see that all the net force will be parallel to the displacement. Means that we won't be seeing situation where the net force is pointing at the direction at an angle from the displacement. For our syllabus, the net force is always in the direction of the displacement or opposite the direction of displacement, because we don't want our object to move in a curved path. If you have your net force pointing at an angle, then you have a net force in the direction perpendicular to the displacement. Then this will cause acceleration in the perpendicular direction, causing the object to move in a curved path. But in our syllabus, we always restrict ourselves to a straight line motion. So a net force is always aligned with the displacement. It's either in the direction of displacement or opposite the direction of displacement. So this is what you usually see if our total work done is positive. Next, for work done total, for your total work done equals 0, it's because your angle between the net force and the displacement is 90 degree. So if our displacement is pointing, let's say, to this direction, then you see your net force either pointing up or pointing down, as what's shown over here. So there's nothing much to be explained for this situation here. If your net force is perpendicular to your displacement, it's a situation which we rarely see in chapter 5, but this situation over here is actually a situation where we'll see in chapter 6. Okay, in chapter 6 you study uniform circular motion where object moves in circles. So for that situation, your velocity will be perpendicular to the force and it will cause you to move in a curved path. So it will be slightly related to this thing over here, but we will not touch this in chapter 6. Okay, just a brief trying to relate to chapter 6. So for the work done total equals to negative value, so your negative total work done, then your angle behind here should be in the range of 90 to 180, but not inclusive of 90, inclusive of 180. So in other words, you should see your net force to have a component which is opposite to the direction of displacement. So if your displacement is pointing to this direction, pointing to the right, you should expect your net force to have a component pointing in the opposite direction, to the left. So it can also be something like this, as long as if you resolve it, the component of the net force parallel to the displacement is opposite the direction of displacement. Then you can say that the total work done will be negative. Okay, so this is similar to the video where I discussed what does it mean when work done is positive, negative, and zero. Just that this time it's a net force version, a total work done version. So let's bring something back from chapter 4 on forces. Chapter 4, I learned that Newton's second law says that net force is equals to mass times acceleration. This is what you learn from your Newton's second law of motion. Then you also know for a fact that your mass is never a negative value. Your mass is always greater than zero because in our level of physics, there's no negative mass. Okay, so knowing these two facts over here, you can recall something from your chapter 1 on scalar multiplication. Scalar multiplication, it's a multiplication between a vector and a scalar. So something like f equals to negative kx or f equals to ma in this case over here. So those are scalar multiplication. As you remember that if the scalar quantity that you have over here, if the scalar quantity is positive, then you know that the net force and the acceleration over here will be pointing in the same direction. If the scalar quantity here is a negative value, then the vector here and the vector here will be pointing in opposite direction. But for now, we know that mass is always positive in our level, so net force and acceleration here must be pointing in the same direction. So why do I point this thing out here is because we know that the net force and the acceleration must be pointing in opposite direction. We know that we can just replace these vector arrows that represents net force here. We can just replace it with acceleration. So what I will do here is I replace the net force over here with acceleration because they are pointing in the same direction. So now I do the switch. So I'm changing the net force to acceleration. So now why do I do that here? Because I'm going to analyze something regarding the speed of the object. So we know the object here is moving to the right, so we can say that the velocity is pointing to the right because the direction of velocity is the same as the direction of motion. So in here your velocity is pointing to the right and your acceleration is pointing to the right. So if the acceleration and the velocity are both pointing to the right, they are pointing in the same direction. So if they are in the same direction, A and B in the same direction, what does it mean? Recall back to your chapter 2 on kinematics. If they are in the same direction, that means the object is speeding up. If the object is speeding up, if you want to talk about it in terms of kinetic energy, that means the kinetic energy increases. So if you have a positive total work done, then your object will speed up. And if your object speeds up, that means your kinetic energy increases. So if in a mathematical form, it means that your delta K is greater than 0. Delta here means change. K means kinetic energy. So change in kinetic energy is greater than 0. Okay, change here is always final minus initial. So delta K here, change in kinetic energy here means it's final kinetic energy minus initial kinetic energy. So if final minus initial is greater than 0, it makes sense, right? Because kinetic energy increases means your kinetic energy final will be greater than your kinetic energy initial. So if something is greater minus something which is smaller, you get a positive value. 5 minus 3, let's say, you get a positive value. Larger minus smaller, you get a positive value. That's why your change in kinetic energy will be positive if your total work done is a positive value. Okay? If your total work done is equal to 0, then you can see that for here the velocity is pointing to the right, but your acceleration is pointing upwards, let's say. So that V and the A are in opposite, are perpendicular to each other. So if they are perpendicular to each other, this velocity here won't change. So your speed will remain constant. Okay, this speed here will not change, but because of this acceleration here, your velocity direction will change. Okay, but this one we'll leave it to chapter 6 when we talk about circular motion. But for now, you know that if the acceleration is perpendicular to the velocity, the speed will not change. The magnitude of the velocity will not change, so it will remain the same speed, but the acceleration here will cause a change in direction. But that's for chapter 6. So if the speed remain constant, we still remember that the kinetic energy should remain constant because kinetic energy is half mv squared. The v is speed, the v is not velocity. So if your speed remain constant, your kinetic energy will remain constant. Therefore, the change in kinetic energy is equal to 0 because the final kinetic energy is the same as the initial kinetic energy. So if you minus this two thing out, you should get 0. So the change in kinetic energy is 0. Okay. For work done total less than 0, or in another word, negative total work done, you see that your velocity is opposite the direction of acceleration. The velocity should be in the same direction as the direction of motion, so the velocity is pointing to the right. But in this case, the acceleration is pointing to the left because the net force is pointing to the left. So the acceleration and the velocity are pointing in opposite direction. So opposite direction means that the object will slow down. So if the object slows down, you know that the speed will decrease. The speed decrease, then your kinetic energy should decrease as well. So if your kinetic energy decrease, that means your final kinetic energy will be smaller. Your initial kinetic energy will be greater. So if you have smaller value minus a larger value, you will get a negative answer. That's why your change in kinetic energy is less than 0. Or you can say your change in kinetic energy is negative. Okay, so what am I trying to tell you here is, if your total work done is positive, your change in kinetic energy will be positive. If your total work done here is 0, then your change in kinetic energy will be 0. And if your total work done is negative, then your change in kinetic energy will be negative. So this will be very important when we move on further in the next video to discuss work energy theorem.